Chapter 4 Entropy. Section 4.7 The Third Law of Thermodynamics. The third law of thermodynamics states that the entropy of a perfect crystal is zero as its temperature becomes 0 Kelvin. Given this zero reference, the absolute value of the entropy of a solid at finite temperatures can be determined with this equation. The entropy at temperature T is equal to the entropy at temperature T minus the entropy at 0K equals delta S. This is because entropy is a state function, and also the entropy of such a perfect crystal is 0 at 0K. So really, if we can determine the entropy change from 0K to this T prime, we should be able to determine the absolute value of the entropy of this solid. When there is no phase change, the exact differential of entropy is this. This is an indirect definition of entropy in thermodynamics. ds is equal to dq reversible over T. dq is du minus dw. dw is negative p external dv, and over here, if the process is reversible, we can say dw is negative p dv. Even if there is a irreversible process that connects the initial state and the final state, you can always mentally redesign a different reversible process and use q reversible there. So that's why we can do this. And du is dh minus pdv minus vdp. Therefore we have this equation. ds is dh minus vdp. Now we're going to expand h. H is a function of temperature and pressure. That's why dH is delta H over delta T times dt plus delta H over delta P times dP. So we have this. What's delta H over delta T under constant pressure condition? It's just C sub P. It's just because dH is equal to dQP under the isobaric condition. What about delta H over delta P? It's V minus T times delta V over delta T. We'll prove this in chapter 5. Now VdP and VdP cancel, we have these two terms. When pressure is held constant, for example, if we have this process under a constant pressure condition, then ds is simply just Cp dt over T. And therefore, the entropy of this solid at T prime is equal to the entropy difference between 0 temperature and T prime temperature. And this difference is simply the integral of Cp dt over T. The third law of thermodynamics states that the entropy of a perfect crystal is 0 when temperature is 0. So given this zero reference, we can also determine the entropy of a liquid at a finite temperature. How do we do this? We can again go from 0K solid to the liquid at temperature T prime. But we need to divide this process into 3 steps. The first step, we increase the temperature from 0K to the melting point. In the second step, the solid melts into liquid at the melting point. Above the melting point, we heat up the liquid. Because entropy is a state function, we just need to calculate the entropy change of the first step, of the second step, of the third step, and then we sum everything up. When pressure is held constant, the entropy of fusion at the melting point is determined this way. ds is dq over T, dq is dq sub P under isobaric condition for a reversible process. Over here, this reversible means, well, when the solid melts, the temperature should be higher than the melting point. But how much higher? What's the difference? The difference should be infinitesimal. Now we have this equation. ds is dH over T fusion, and then delta S fusion is simply the integral of this. Because the fusion temperature is constant, it's just the melting point, so we have the integral of dH over T, which is delta H over T at the melting point. Again, at the melting point, delta H fusion is the melting point times the entropy change of fusion. T fusion is just the melting point. Again, because entropy is a state function, the entropy of the liquid at temperature T prime minus the entropy of the solid at 0K, so this is actually 0, is equal to the sum of three terms. In this first term, we increase the temperature of the solid from 0 to the melting point. In the second step, we look at the entropy of fusion, which is delta H of fusion over T of fusion. Third step, we increase the temperature of the liquid from T fusion to T prime. Sorry about this mistake here. This should be T prime. The third law of thermodynamics states that the entropy of a perfect crystal is 0, and therefore we can even calculate the entropy of a gas at a finite temperature. We just need to convert the solid at 0K to the gas phase at temperature T prime, and T prime is higher than the boiling point. And in this case, we need to divide the entire process into 5 steps. In the first step, we heat up the solid. In the second step, it's the fusion process from solid to liquid at a constant temperature, the melting point of the substance. And then between the melting point and the boiling point, we heat up the liquid. At the boiling point, we vaporize the liquid into gas. Above the boiling point, we heat up the gas. Therefore, there are 5 steps. We just need to add up the entropy changes of all these 5 steps. The first step, we heat up the solid. In the second step, fusion. Third step, we heat up the liquid from the melting point to the boiling point. The fourth step, well, we vaporize the liquid into a gas. The last step, we heat up the gas. Again, when there's no phase change, ds is Cp dt over T under isobaric condition. Therefore, you see this integral of Cp dt over T for solid, Cp dt over T for liquid, Cp dt over T for gas. At the melting point, delta H fusion equals T fusion times delta S fusion. So delta S fusion is this delta H over T. At the boiling point, delta H equals T times delta S as well on the isobaric condition. Therefore, over here we have the entropy change of the vaporization process. Again, at the temperature of a phase transition, delta H is T times delta S. This T is the temperature when this phase change or phase transition occurs. Delta H and delta S are the changes of enthalpy and entropy in this phase transition under isobaric condition. Under isochoric condition, which is extremely rare, we have delta U equals T delta S. Now we're going to analyze the entropy values versus the entropy values of a gas versus the entropy values of a liquid and the entropy values of a solid. In general, the molar entropy of a gas is greater than that of a liquid, which is in turn greater than that of a solid. It also entropy increases as temperature increases. And there are more rules that help us compare the entropy of different chemicals. A weakly bound matter always has a greater entropy than a strongly bound one. Therefore, the transition state of this reaction has a tighter structure and thereby a lower entropy than the two separated reactants. The transition state of this reaction has a structure with hydrogen atom in the middle, partially bonded to chlorine and partially bonded to bromine. This transition state structure is more tightly bound than two separate chemicals. Here's another example. The transition state structure of the Diels order reaction has a tighter structure than two separated reactants, and therefore lower entropy than the two separate reactants. The entropy of a system increases as the number of microstates increases, and therefore molecules with more vibration modes have a higher entropy than the ones with fewer vibration modes, because we have more vibrational entropy. Molecules with more atoms have more vibration modes and therefore higher entropy. Here's one example. Ethane contains 8 atoms, methane 5 atoms. Therefore, the molar entropy of ethane is greater than the molar entropy of methane. Ethane has many more vibrational modes, therefore higher vibrational entropy. Propane has higher molar entropy than ethane for the same reason. For noble gases, heavier atoms have smaller translational energy spaces and thereby higher entropy than lighter ones. Therefore, neon has a higher molar entropy than helium. Argon has a higher entropy than neon. For similar molecules with the same number of atoms, heavier molecules always have higher molar entropy. For example, this is tetrabromide. This is carbon tetrabromide. It has a higher molar entropy than carbon tetrachloride. This is just because the heavier molecule have higher translational entropy. And also, a heavier molecule often has a higher rotational entropy as well. So overall, heavier molecules have a higher entropy than lighter molecules if they have roughly the same structure.